Great. Thanks so much, Karen. Thanks you to everybody. Thank you to the organizers for inviting me. It's really been fascinating. You guys have such a wonderful country here. I've been here for about a week so far, exploring just the North Island so far, and it's really been wonderful, and I really appreciate the opportunity to come down and to speak to all and just to enjoy your natural wonders here. As Karen had said, yes, a lot of our research, certainly not all of it, but a lot of our research has centered on queens and ways to improve their reproductive quality. This is through breeding, it is through manipulation, management, and other practices. And after 30 years of such research, I pose this question to you just as much as you would pose it to me, and that is, what's going on with queens? And for those of you that don't want to listen to me drone on for the next 30 minutes or so, I can give you the punchline right now. I have no idea. I don't know what's going on. 30 years of research, and we still kind of just scratching at the surface. And I think that Oksana had set me up very nicely earlier this morning talking about some of the issues and some of the things that we're seeing, and it's actually nice to know that in some ways that you guys are seeing the same thing, so my talk here is not going to be completely North American biased. But to emphasize what was discussed this morning, looking at many of the surveys, this is done by the Pollinator Partnership, there's the laser. The Bee Informed Partnership, which has been doing these surveys since colony collapse disorder really hit the headlines, as Peter had mentioned earlier this morning. They too have been doing these surveys, these beekeeper surveys, and asking the beekeepers, what are some of your top reasons that you attribute to the colony losses? And consistently among those top reasons is some sort of queen failure or queen problems. That roughly between 20 to 25% of the colonies that die in the US every year, of which about 40% are turning over and dying every single year, so higher mortality rates than what you guys have here, about 20 to 25% of the colonies are experiencing some issues with queens. So it really is a top management concern, and in fact, a lot of the other ones above that, like starvation and the weather, and these are things that are a little less out of our control as beekeepers. But queens, that's definitely something managerial, definitely something that we have control over. And so this is a good target for trying to improve colony losses, that is, reduce colony losses, by trying to mitigate these potential queen problems. And some of our research has shown that colonies that experience queen problems, queen losses, or queen failure, are 3.1 times more likely to die. Because if a colony has an issue with its queen, then that then introduces a lot of these other stressors, and it adds to all of these other things that we as beekeepers are dealing with, and there's this cascade effect which then makes those other issues a lot more difficult to address, and therefore colonies are 3 times more likely to die. Now, what is the solution then to these queen problems? And I like to use this quote by Menkensen, saying that for every complex problem, there is a clear, simple answer that is just dead wrong, right? And this is very true when it comes to queens. There is no one answer to why we're having queen problems. There's multiple reasons. And so I just want to explore some of the research that we have been doing to try to get to this answer, this kind of multifaceted answer, in an effort to try to come up with ways to mitigate those problems. Now, one nice thing about apiculture research is that we've been doing it for 2,000 years or so, and so there's always a literature upon which we can draw to be able to compare what's going on today to what beekeepers had been experiencing, a generation or so ago. And when it comes to queen problems, there's actually a very nice literature that we can draw on going back all the way to the 1940s, where we have a baseline of what queens used to look like. And then if we compare the queens today to see some of these different measures of queens and their reproductive quality, we can say, here's kind of that smoking gun. Here's this one thing that is different from the way that it used to be, and therefore we can focus on that in a way to improve our queen quality. Well, to spare you about 15 years or so of research, we are looking at the queen physical capacity to lay eggs, diseases, and their mating, insemination and mating success. And to sum all of that 15 years of research up, none of those measures seem to have fallen off a cliff. We were expecting to go in and measure these different queens and find that they had far fewer sperm counts than they used to, or far higher levels of nosema than they used to, or far, different measures than they used to. And in fact, that's not what we found at all. The queens, these commercially produced queens that were part of these different studies, seemed to all be of high reproductive quality. So our hope in going into this was trying to identify some obvious smoking gun, and we failed at that. What was nice outcome of this, and Karen had mentioned this, is that based on that empirical research, we now have a good baseline of what makes a good queen good and what makes a bad queen bad. And we now offer this as an extension service to our beekeepers in North Carolina and beyond, where we have this queen and disease clinic where especially queen breeders, but really any beekeepers can send in their queens and we can measure them in the same way that we do in our empirical studies, and we can grade them. We can put them on this kind of standard measuring stick, and we can give a letter grade, because we're at the university after all, right? So we have to give letter grades. And so we can empirically and objectively measure queens, and we can say where they rank on that standard measuring stick, and we can get very granular, and we can drill down and say whether it's some sort of physical ailment or some sort of insemination impediment or insemination problem like lower sperm viability in the queen spermatheca or something like that. So we're able to do that thanks to Brad Metz and Lauren Paterzo. They're the two technicians that are running the queen and disease side of the clinic respectively. And we're able to generate these reports on queens in near real time. So if a set of queens comes in, we can usually turn that around within 2 days or so that beekeepers can make management decisions based on the results that they find, because a lot of these queen issues are invisible to the queen producers. And so a lot of our clients that we work with are kind of larger scale commercial queen producers where they're producing 10,000 queens a week or so, and if they send us 20 of them, we would be able to then tell them, give them this letter grade of how good their queens are, so that they would know the other 9,980 other queens that they can sell of what kind of relative reproductive quality that they have. So it's been very effective and very worthwhile. But as I said, a lot of our empirical research trying to pinpoint this one smoking gun, and we haven't really been able to find it. So this has kind of made us scratch our heads and to go back and to say, okay, well, what really is going on with queens? Why are we experiencing 20 to 25% of colony losses because of queen problems, but we can't really find anything wrong with the queens themselves? And so this is kind of to step back and to look at these potential issues. I think it's, again, very complex and very interactive, where there's many different biological, chemical, management, and environmental issues that are going on that affect queens. And if we look at these surveys, or at least the ones done by the Bee Informed Partnership, I think a lot of the queen problems tend to be collapsed into one category, but there's actually many different things going on. And for the sake of discussion and purposes here, I just want to talk very briefly about 4 of them, because I would submit to you that they are all very different in their causes and their potential solutions. But they're still captured under this kind of queen problem umbrella. The first is the queen physical reproductive capacity of herself. That is, she is just not up to the task. But another, as was mentioned earlier, is the bad brood pattern of the queen, which is how most beekeepers, I think, identify and diagnose a queen problem. The third is what that queen is laying, so premature drone laying. And then finally, premature or early supersedure. So these are kind of 4 different problems that all have different root causes. And so we'll discuss that very briefly here if we could. The first is the actual poor physical or mating quality of the queens themselves. And this is where understanding the biology of queens is really, really important, because queens, and there's only 1 per colony, of course, is actually not genetically different whatsoever from the workers. And if you think about it, what we have are the 2 ends of a continuum of female honeybees. Queens are the most fecund and are reproductive. Workers are the facultatively sterile and they're non-reproductive. But in actuality, you can produce everything in between. You can produce these intercasts very readily by grafting older worker larvae, right, which have spent 2 or 3 days in worker development already, so when they're started to fed royal jelly later on in their development, they still become queens, but they're more worker-like. So you have this entire continuum from queens to workers. Depending on when you actually graft that larva, you can kind of make all of these intercasts on purpose. Now, I don't recommend that you guys do this yourselves, obviously, but we as scientists, we like to meddle and we like to, kind of come up with these pseudo-mutants within colonies to really inform us of what makes a bad queen bad, to help us inform of what makes a good queen good. And so we've done this. We've made the best possible queens that we possibly could. Grafting the youngest possible larvae that we could. And we also purposely made the worst possible queens that we could by grafting 3-day-old larvae. So these things are very, very worker-like, and they're just kind of runty and small, and they don't mate as much, and they're just not very good queens. And then we place these colonies out into starter swarm packages, watch those colonies grow over the course of the growing season. And sure enough, the colonies headed by these higher quality queens were more populous and had more brood and built more comb and everything else than those headed by the lower quality queens. But if you see, the difference between those things are statistically significant, but they're quite subtle. So the way that I like to look at it, and the way that you should take home from this, is that if you have a poor queen, that is, she is smaller, she didn't have as much sperm, well, she's only going to make the colony, she has a low ceiling as far as the colony is concerned, right? But if you have a higher quality queen, you're going to have a higher ceiling, so the productivity of the colony and the colony growth and everything else is going to be higher. But it's not like astronomically different, right? So the quality of the queen within your colonies is very important, but it's also very subtle. It's not kind of cut and dry. So then that leads us to the next issue, which again, I would submit to you that most of us as beekeepers are kind of diagnosing queen problems by looking at the brood pattern. So we've had it in our heads since we first learned beekeeping that, this is another very quick side note. We've been able to manipulate the queen rearing process just a little bit by supplementing the brood food, the royal jelly of queen cells, and making queens 20% larger than what you can make in nature, or what the bees will make in nature. And so we do this through added sugars and juvenile hormone right at the right stage of development. And that allows those larvae to just eat a little bit more and grow a little bit bigger. And so we can make what we like to call super queens. And these super queens then are, again, 20% larger and more fecund than the highest quality queens that we can raise. We still, however, need to make sure that these super queens are going to make better colonies, and that just because they're bigger doesn't necessarily make them better. In fact, there's a possible reason to think that these queens are so big that their butts can't even fit in the cells anymore and they can't lay eggs, right? So we need to finalize that this actually has colony level effects. But the super queens is something that we find very exciting and look forward to further research on that. Okay, so the brood patterns is how we tend to diagnose bad queens. So this is the American term, at least, shot brood. Does that mean anything to you guys? Shot brood, that's the term here. It looks like you just take a shotgun and you shot a nice frame of contiguous brood. We're really into guns in the US, right? So maybe that's why. But there is a reason for this. There is a reason why shot brood has been tied to poor queens. And that comes down to a very simple genetics. A single gene is responsible for whether a bee turns into a male or a female. And so apologize for those of you that already know this, but in essence, there's a single gene with many different forms of that gene or alleles, like a dozen or 24 of these different forms. Think of it like eye color, right? Where you have a single gene for eye color, but we have an allele for brown, an allele for blue, an allele for green, hazel, so on and so forth. And so when a queen mates with a drone that has a different allele at this particular gene, when she fertilizes these eggs, they all have 2 different forms of this gene. They all are normal, and they become workers. So you have this perfect brood pattern within the colony because all the eggs that she lays and fertilizes turn into females. By chance, by bad luck really, if a queen mates with a drone that shares one of her 2 alleles that she has, half of the eggs that she fertilizes, rather than becoming workers, they become drones. But they're fertilized, so they're diploid drones. You've heard this term? Yes? And they're kind of like frankenbees. They don't really exist in nature. And they get cannibalized during early larval development. So the queen's going along, laying eggs, fertilizing them like normal, but if she just kind of mates with this dud of a drone, the half of those offspring are lethal. They get cannibalized by the nurse bees. So she thinks she's laying a good brood pattern, but you go into the colony and you have this shot brood because every other egg on average was inviable. So this is how we've got it in our heads that a bad brood pattern equals a bad queen. Because queens do not remate ever in their lives, she's never going to be cured of this condition, and therefore you might as well just get rid of her, replace that queen, and Bob's your uncle, right? That's what you say around here, Bob's your uncle, that's what I've heard. The problem with that is that now I think we've had it in our heads as beekeepers, or at least those of us in the US, whenever we see any bad brood pattern, we're like, that's a queen problem, get rid of her. But you can get a bad brood pattern lots of other ways, right? So here's a good example of parasitic mite syndrome, which was brought up before, or idiopathic brood disease syndrome, or IBDS, which is in essence parasitic mite syndrome without the mites, right? Because it's mostly driven by these viruses that the mites are vectoring. So you can have control of the mites within your colony, but they've already done the damage by spreading all of these different viruses, and so you get these bad brood patterns, but without the mites. But it's not the queen's fault, right? It's something else going on inside the colony. So we did this study with Marla Spivak's lab with Katie Lee, who I would encourage you to bring down any chance that you might be able to get. She's still at University of Minnesota. Well, we were looking, again, for this silver bullet of bad queens versus good queens, and she was going through a lot of these commercial operations, And every time that she would find a bad queen, as identified by one having a bad brood pattern, she would sample that queen, take some wax for pesticide residue analysis, take some workers for colony-level pathogen analysis, and then send the queen to us, and we'd put them through that kind of reproductive quality analysis. And then she would go to the colony right next door, where it had a perfectly good queen, and she'd sample that queen and the wax and the bees. And so we were looking to see if we found anything in the bad queens that we didn't find in the good queens, or vice versa, as an indicator of what might be driving these bad queens. And unfortunately, we didn't find anything consistent. In one operation, we found it was a potential virus problem. In another situation, the bad queens had bad sperm viability. In another situation, there was one pesticide that was found that was not found in the healthy colonies. So there was nothing consistent. And so disheveled, the following year, we were just going to redo it in hopes that we might have a bigger sample size, we might be able to find something. When Katie came up with a real stroke of brilliance, she said, well, rather than just sampling them and measuring them again, why don't we just swap them? We'll take the bad queen and take her from the bad colony and put her in the good one, and vice versa. And so if it really is the queen's problem, if the brood pattern is a function of the queen, then the brood pattern in the good colony should go down because the bad queen is in there now, and the brood pattern in the bad colony should go up because the good queen is in there now. And we did that, looked after a full brood cycle, and found that that was not the case. In essence, the brood pattern in the bad colony stayed pretty much bad, and the brood pattern in the good colony stayed good. It really wasn't driven so much by the queen itself. So there's one take home from this, is that we need to dislink this whole thing of diagnosing queen problems from the brood pattern itself. Because if you think about it, yes, the queen lays the egg, but who raises that brood? It's the workers. It's kind of like what Peter had said earlier, nothing in honeybee biology makes sense without, the context of the colony. And so the queens are getting blamed, but it's actually the workers that are raising that brood. And so we need to kind of disambiguate those things. All right, the third issue that I talked about is not just the pattern that the queen is laying, but what she is laying. And a lot of the problems that beekeepers have been finding is that they run out of sperm quickly. In other words, they aren't able to fertilize those eggs, not just fertilize with the wrong drone, but fertilize them at all. And so a lot of times you get something like this, where you have a brood pattern where you have all of these these drones in the middle of the brood nest where the workers ought to be and not on the periphery where they should be. And so, you can see something like this where every single egg is a drone, and therefore that's an indication that the queen just never mated properly, or she has, a spermatheca that's empty, so she's incapable of fertilizing those eggs. That is different from something like this, where you might have a similar brood pattern, but a little bit different in the sense that you have an increasing frequency of drones within the brood nest over time, where the sperm in the spermatheca has died, and so she's unable to fertilize the eggs with live sperm. So she might have been good at one point, but she kind of goes downhill quickly because she's used up all of the live sperm in a spermatheca because the sperm in there has died for some reason or another. So these are different phenomenon, right? This is just poor mating. She just never mated with any drones. This is that she mated and she was good at one point, but she is running out of live sperm, either because she's old or she was exposed to something that killed off the sperm in her spermatheca, so she's no longer able to fertilize those eggs. So again, those are very different things, and being able to distinguish those between those is really, really important. And then fourth and finally, premature supersedure. Do you have this phenomenon in New Zealand at all? Queens are not living as long as they used to. There's anecdotal evidence for this, but not really a lot of empirical evidence. The best I can come up with is a very, very poor comparison. Looking at a population of queens from Canada, which is practically the North Pole, they looked at queens in the 70s and 80s, and they were marking their queens so they knew how long they lived. And if you just kind of draw a line at the median survival of queens, in northern Canada, they lived over 2 years. So that was the median age of queens back in the 70s and 80s. We did a similar study in North Carolina on 2 different stock types, and what we were finding is that the median age of queens was less than 1 year. And this was done in the mid-aughts. And so if you compare these apples to apples, there seems to be a decrease in survival of queens by 50+% over the last few decades. Of course, they're not apples to apples because they're in different geographic locations, different genetic stocks, so on and so forth. So take that with a huge grain of salt. But if you talk to beekeepers in the US, anecdotally, have been keeping bees for decades or more, they will say that they never used to have to requeen their colonies on a regular basis, maybe every 2 or 3 years. But it was very often that they would find queens that were living 2, 3, 4 years. And now beekeepers, especially the large-scale commercial beekeepers, are requeening their colonies every single year, if not twice a year. So there definitely is something going on with decreased longevity of queens, even though we might not have the empirical baseline data to show on that. So colonies are replacing their queens, or the queens are just not living as long, and we're not really sure why. I go back to this study with Juliana Rangel when she was a postdoc in the lab, where we're looking at high and low quality queens. And one thing that we predicted is that these low-quality queens, they were really bad, right? They were just bad queens, and we made them bad on purpose. And we expected the workers to recognize that these were just junk queens, and they were going to supersede them and get rid of them much more quickly. And in fact, that's not what we found. That the high-quality queens and low-quality queens were replaced at about roughly the same rates, which was fairly low. So, we know that this queen is bad, but the workers don't. But then in our beekeeping operations, we think these queens are good and the workers are replacing them. So I don't know what's going on with that, but it's clearly an important and interesting phenomenon. So what are some of the kind of stressors and abiotic and managerial issues that we've been studying that can result in these poor queens? Just as some examples. This is Allie McAfee. She's a postdoc in our lab, but she's actually located in Vancouver, Canada. And she's been looking at both the proteomics as well as the effect of temperature on queen and drone sperm viability. So queens in their stored spermatheca and drones in their seminal vesicles. It's long been known that if you overheat queens or colonies, they die. Right? You know that if you kind of suffocate them, or they can easily kind of get too hot and the queens die. Or just before they die, the sperm in the queen's spermatheca all dies off. And so a lot of us, at least in the US, we tend to overcompensate and make sure that the queens are nice and cool during shipping and during handling, so they don't die. But what she has found is that if they get over-chilled, the spermatheca in the sperm in the queen's spermatheca die as well. So you need to be very careful in handling the temperature of handling your queens and shipping your queens. Because if they get too hot, the sperm in the spermatheca will die, but if they get too cold, they'll die as well. And so only live sperm can fertilize eggs, and therefore, once she runs out of live sperm, she will not be able to live as long. So, sperm viability is a major predictor of queen longevity. So just keep that in mind as you're handling your queens. We're looking at the same effects of temperature during shipping in packaged bees in the US, where we would load up a whole bunch of queens with temperature probes on their cages in these packages and then hived them up when they got to their destination. And what we were expecting is that the queens in the packages on the outside were going to get more exposed to the elements and therefore get chilled more and therefore had lower sperm viability as they were hived up, and those in the middle were going to be warmer. That wasn't what we found at all. There was plenty of air circulation within these truckloads of packages. And so we just saw that, there were queens that were exposed to hot temperatures, queens that were exposed to cold temperatures. And when we hived them up, about 25% of the queens were superseded within the first 8 weeks. But it was not a function of their temperature exposure during shipment. So while temperature may have an impact on queen longevity and sperm viability, it's certainly not the only thing. So we need to drill down more into this, but it does show that we need to be cautious in our management and in our handling of queens during shipping. Now, one last thing, because I realize I'm running out of time, I want to talk about the effects of pesticides on queen reproductive quality. So this is Joe Malone. He was a PhD student in our lab for several years. He's a toxicologist. I am not. So he really did a lot of this research looking at the effects of pesticides on queen quality that really opened my eyes. And there are two major routes by which queens can get exposed to pesticides. One is during development through the wax, right? So there's something like 9 or so different common pesticides that are found on average within beeswax that can leach into the royal jelly during development. The other is through the nutritional route through pollen. So pollens can be coming into colonies. The average number of pesticides in the US coming in through that route is about 11. And so we fed colonies with contaminated pollen patties or not, and contaminated wax or not. And so all 4 of those combinations, and looked at the reproductive quality of the queens. The take home is that if the wax had pesticides in it, the colonies just didn't raise as many queens, but the ones that resulted were of similar and high enough reproductive quality. So they tend to cull out the queens if they're in kind of a pesticide environment, rearing environment. For the food contamination, what that had was that it didn't affect the number of queens that were reared, but it did affect the reproductive quality, where they did not have the same sperm counts and body size and those kind of things. But when we looked at the pesticides in the royal jelly of those treatment groups, of the ones that were fed contaminated pollen, what we found was shockingly no pesticides in the royal jelly. So the queens were of lower reproductive quality if the colonies were fed pesticides, but they weren't exposed to the pesticides themselves, which is a real head scratcher. So what we did is we teamed up with Priya Chakrabarty, who was a proteomicist at Oregon State University. And the take home here was that the quality and the quantity of the royal jelly in these colonies that were fed these contaminated pollen patties, they were taking a hit for the team, right? So they were providing lesser royal jelly and less of it. And that's why the queens were of lower reproductive quality, but the queens themselves were not directly exposed to these pesticides. So it really shows these kind of complex and indirect routes of pesticides and how it affects our colonies without us really knowing it. So it's not a direct effect, but rather an indirect effect. So I'll just end with kind of stepping backwards again and saying, well, why do good queens go bad? There is no one answer. It is all very contextual, but I would submit to you that bad queens, or at least the way that our surveys and the way that we're thinking about bad queens, is that bad queens are actually more of a symptom than a cause. So if we look at the reasons why it's the fault of the queen or the fault of the colony, A lot of times it's both, or really the colony environment in which the queen is placed, rather than the queen actually precipitating the issues within the colony. The queens are getting blamed. They're not the reason why they're having problems. And so I just want to make sure that I thank all of the excellent collaborators and funding sources who were responsible for helping us facilitate a lot of that research. And I'd be happy to take any questions or turn it over to the panel for our Q&A. Thank you very much.